Swayam Prabha. Digital India. Educated India.
So, let us begin again our discussion on phase equilibrium. That is another part that we are considering here, that is how to draw the phase diagram. That is, we have learned that when there is a phase transition, if we change the temperature, the pressure has to be changed in such a way that we can restore the system to a new equilibrium. Then we can find out the P versus T curves. So, that is the thing that we need. So, to discuss this phase diagram, they are basically the P versus T curve. So, how those P versus T curves can be drawn, and the clue lies in basically the same Clapeyron equation. So, we start from the Clapeyron equation that we introduced last time. So, starting point again. So, starting point again is a Clapeyron equation. So, it tells us that the pressure of the system is changed by dt, then dPd has to be changed in such a way that is it is equal to delta S molar entropy change between the phase divided by delta molar volume change between the two phases. So, that was the starting point for our discussion. So, if this is so, then we take the for each case of transition between the phases separately. So, what we are going to do here is the following. First, we take this delta S by delta V for separate cases. That is, we first consider the solid to liquid, so or melting process, that is solid liquid transition. So, in this case, we first take note that del S is basically something to do with del H. Again, solid to liquid is basically that describes the fusion. So, this is for fusion, that is equal to fusion divided by T, and this means that del S fusion by del V fusion equal to del H fusion by T times del V fusion. Now, if we compare this solid liquid transition with the liquid vapor transition, then something will come out. So, this delta H is for fusion and delta V is again for fusion process, that for which the system goes from solid to liquid phase. That and for liquid to gas phase, gas transition, we have the same thing, that is delta S of vaporization equal to delta H for vaporization by T, and delta S for vaporization divided by T into delta V of vaporization. So, if you compare and sorry, this should be delta H by S. So, I need to write delta S of vaporization divided by delta V of vaporization equal to delta H of vaporization divided by T delta V of vaporization. Now, you compare these the quantities on the right hand side here and this quantity. So, this delta H of fusion, if we take the delta H of fusion and delta H of vaporization, they are nearly of same order, not that different. So, if the delta H of fusion and delta H of vaporization are nearly of the same order, that means if this is so, now if we compare the two in the what are there in the denominator delta V, so comparing, so delta V, or if I write it delta V for fusion is much less than delta V of vaporization. Say it is much greater than this. So, if it is much greater than this, that means the slope, if I plot if I plot P versus T, then the slope for the fusion curve will be much larger, because there the denominator is very small. So, this means, this implies delta H by fusion by T delta V of fusion much greater than delta H of vaporization divided by T delta V of vaporization. So, this means that, so dP by T for P versus T curve, so for the P versus T curve, slope for fusion curve will be steeper than that for the vaporization curve. So, if we plot P versus T, what should be the thing? So, it is P versus T. So, P versus T has a, so there is a slope like this. So, this is the solid liquid, this is solid liquid transition, and this is much, and this is for liquid gas transition. So, it is much stiffer compared to this. So, this gives you the solid, this is liquid and this is gas, and of course, they will meet at some point. If they meet at some point, at here solid, liquid and gas phase coexist. It is basically a triple point. Now, there is another case. This is not the end of the story. Then there is another case. If I go from sublimation case, that is directly from solid to gas. So, what should be the thing? So, delta S for sublimation, delta S for sublimation is equal to delta H for sublimation divided by T. That is the, now delta H for sublimation means what? Means it is basically a solid goes directly to the vapor state or the gaseous state. So, there is a, so if you take care of the stage wise process, then it includes delta H for fusion first, that solid to liquid fusion, then it will go directly to vapor. So, delta H for vaporization. This takes care of the transition for solid to liquid, and this is for the enthalpy change for liquid to gas. So, this delta H, that is the enthalpy change for solid to gaseous phase, must comprise of these two terms. So, that means it is so if instead of vaporization, if you put the sublimation here, so the curve, that will make the curve slightly stiffer. So, it will be stiffer than this one, but cannot exceed this one. So, it would lie somewhere in between. So, this means that, so the slope of PT curve will be steeper than for this one. So, therefore, I can draw a line here. So, this gives me a solid to gaseous phase direct transition from here to here. So, that and this is basically the triple point corresponding to a definite pressure and at a definite temperature. T is the triple point, and this is the pressure at the triple point, say pressure at the triple point. So, this is an unique point, as you see that it is characteristic of the system itself. So, the slope for P versus T curve will be steeper than the PT, than that for the for PT curve for the vaporization curve. So, if this is so, this curve means that any point in this PT diagram is defines a state. Any point. So, here at any point, so any point in the phase diagram denotes a state of the system. Any point. So, any point in this region is a solid state, is a solid phase, and any point in this region is a liquid phase, and any point here is basically gaseous phase. Now, if you increase the temperature and also the pressure unrestricted, so you can increase it, but there is a limit. So, P versus T curve can continue, but there must be a limit to it, because at some point of pressure and temperature, one cannot distinguish between the liquid and the gas phase. So, one cannot draw PT line for gas liquid transition without a limit, since beyond this limit one cannot distinguish between the phases. So, that has to be kept in mind also. So, these are basically the features of the thing, and features of the PT lines, and so you cannot go on extending at very high temperature and very high pressure. Of course, can you use actually we discover many new phases of the system if we change the pressure or the temperature. That is true, but that is not an unlimited thing. So, there must be some limit, because beyond which we cannot go, because of the fact that at that point of time there is no point in distinguishing the liquid and the gas phase. So, that has to be kept in mind. So, these are this is the important thing, and this is the triple point, and so the left of so it means that for any, it is say 1 atmospheric pressure, I know this is the, so the say the line, solid liquid line. So, the line which demarcates between the solid and liquid, this is basically a coexistence curve. It means that if you vary the temperature, the coexistence point will move along this curve. So, it is basically a locus of all PT points along these lines. So, that has to be kept in mind. So, that is so this is if I look at the normal boiling point of 1 atmosphere, say I have in 1 atmosphere, then I have a normal normal point, melting point, and at this point it is a normal boiling point. So, if it is 1 atmosphere, then we may have, this may be a T melting, this is T boiling point. This is a normal boiling point. And as you go along, so the boiling point will change according to the pressure. So along this line, and melting point will be changing along this curve. And also this the system go over directly from the solid to this solid to the gaseous phase if we lower the pressure to a definite extent and at very low temperature. That is also possible. So these are the typical features of the phase diagram, and we call it a typical phase diagram for any general substance. Nothing, I have not done anything for any specific case, but before completing this part, I will draw two important cases which are well known, and well known for because many experiments have been done on it, on the phase diagram. So we will go for this particular case. We will first take up the case of carbon dioxide, phase diagram of carbon dioxide as an illustration, an example. First example of a phase diagram, carbon dioxide. As usual, that is the pressure temperature curve, and we have again we know that if you follow this prescription, it means that you the solid liquid line that can be obtained for, if you consider this, the fusion delta H for the fusion divided by T times delta V, and again it is a very steep curve, and delta V is always delta V is positive. That for positive delta V, and which is not very large, basically small, and for definite delta H by T, this is the slope. So I can write this as here, the same kind of thing, and this is the triple point. Since I am considering the specific values, I need this breakage point to show that what I am drawing is not really the completely linear curve. So for this, what we do, I will write it as exactly in the solid, liquid. This is the solid phase, liquid phase, gas phase, as usual. Now this is again the line between the solid and the liquid. Now these are the point. This is the triple point. So triple point lies at 5 point. So 5.11 atmosphere. This is in atmosphere. So under 5.11 atmosphere, and temperature is basically minus 56.6 degree centigrade. So this is a triple point. Now another point is that, so if you keep the pressure very high, say it is 67 atmosphere pressure, then I can store my carbon dioxide in a cylinder at a temperature 25 degrees centigrade. That means I can store the carbon dioxide at 25 degrees, that is the normal temperature, at a very high pressure corresponding to this corresponds to this particular point. And you see, below 1 atmosphere, it goes over directly, say around this point, it is say 1 atmosphere. So below this point, it goes straight to the gaseous phase. and below certain temperature, say it is minus 78.2 degree centigrade. So at this point and 1 atmosphere, you see that there is a there is a complete transfer between the solid to gaseous phase. So below 1 atmosphere, the carbon dioxide can exist, and you know that it's called the dry ice. So that is something that is already known. So this is one of the typical cases, the typical phase diagram for practical consideration, and this is one. And we may go over to another case, that is for water. P versus T. Another point we might note here, that since this is a curve, this is a positive slope. So because of the positive slope, if we increase the pressure, the temperature will increase. That means along this curve, if you move from lower pressure to higher pressure, the melting point will increase. So this curve shows that for higher pressure, melting point will increase. That we can see easily, that if we go over in this direction, that is, if we increase the pressure, we move along this line, that means the boiling, the melting point increases. Now you see that for the water is a peculiar object. Example 2, water is a peculiar object, and solid to liquid, when it goes over to solid to liquid, that means V liquid minus V solid is less than 0. That means delta V here is negative. So if you have an ice, when it melts, volume decreases. So liquid minus solid is a volume of the liquid minus solid is a negative quantity. So if this term is negative, then what happens? If this term is negative, then the entire slope, this slope becomes negative. Slope is negative means I cannot have a positive slope like this, but I have a negative slope here. So that I have a slope is somewhat negative. And the other case, so liquid to gas transition curve remains almost the same. And again, this is the solid gas curve. So can go still further. So the curve between, so one important distinction between the carbon dioxide and water is this the solid liquid curve in the two cases has different slope. It's the positive slopes and negative slopes. And if we take care of the details of this thing, then at 1 atmosphere, then say at 1 atmosphere, so if I write it, so it is 1 atmosphere and 100 degrees centigrade. This is solid phase, this is liquid, and this is the gaseous phase. So this is the melting point, this is the boiling point, liquid gas, and this is the this is the melting point, which is much lower. So, for here this is the melting point, as you know, it is 100 degrees centigrade, and this is practically a quantity which is basically 0.0002, almost 0 degrees centigrade to be accurate here, and the triple point that lies the triple point that lies here, it is at 0.01 degrees centigrade. At the pressure is 611 Pascal, and this is of course 1 atmosphere means 10 to the power, this means of the order of 10 to the power 5 Pascal for this. So, this is a typical case, and if we go on increasing the temperature, we will see the at a very high pressure and temperature, we will find the new phases here, that is at 374 degrees centigrade and pressure 220 atmosphere. So, at this point you have several crystalline modifications of water that is possible because of the high, very high pressure, 220 atmospheric pressure, there is possible. And one more thing that is important here, what is the consequence of this negative slope? So, that means that if we increase the pressure, if we increase the pressure, if we go from here to here, the melting point drops. So, here the melting point increases. So, here the difference between the two curves is that with increase of pressure, the melting point drops. That means melting point decreases, and it is because of the negativity of the slope. This is because of the negativity of the slope. So, these are the typical features that we can think of, we can work out for water. Actual phase diagram of water is extremely complicated, much more complicated than this. There are many phases, but for the time being, for an introductory course, I actually try to omit those parts and just kept only the parts which are quite general and should be known to everybody. So, that is the thing that we tried to show here for the two practical cases. And you see that you go through the books, then you will see that you have many phases of sulfur and other things are there. So, they are the functions of temperature and pressure as usual, and they can be, the phases can be, the equilibrium basically can be manipulated to have new and new phases. So, with this I thank you all for your kind attention, and we will move on next to the phase rule, which is an important point or a central point in phase equilibrium. Okay, thank you all.